You're listening to the Red Pill Society with Dr. Clark and the boys. Now here are your hosts, Chris, Brett, and Dr. Clark.
All right, welcome to the Red Pill Society podcast with Dr. Clark. We're going to talk about all things dementia and a lot of his findings. It's going to be a really interesting show. I'm looking forward to it. Dr. Clark, I think the biggest thing is we need to sort of break down what dementia is, because you say it's sort of a general term for all memory cognitive decline, kind of like an infection, there's lots of different kinds of infections, and you were saying like there's lots of different kinds of dementia. It's like a broad sort of encompassing term for a lot of different neurologic diseases.
So yeah, I would call it an umbrella term. Yeah, dementia is just a general term for people who are losing their cognition. And it can be 1,000 causes. It could be, you see it in patients that are chemotherapy patients. You see it in patients that are septic and chronic infections. You see it in just chronic disease processes. You can see it in microvascular stroke. So the vessels that feed the brain are, you can see the big clogs in the big vessels, but you can't see the tiny capillaries. Well, that feeds the brain. So the microvasculature, when it begins to get calcifications in it, then you get the same neurologic damage that you get with just the general Alzheimer's and the other things that we always think of when we talk about dementia. So if you start losing cells in the brain, you start losing cognition, you start losing memories, you start losing the ability to remember how to get home from the hospital or from the store. So, and even why you even came into the kitchen. So no matter what you call it, what the cause is, you still call it a dementia.
Okay.
What external factors contribute to dementia? So what things over the course of your life could you be doing or should you be avoiding that could be causing dementia?
Like, should I not drink so much or smoke too much,
right.
or or go to rock concerts and headbang,
like
all
have
the time.
too much fun, so to speak. But or are you just genetically predisposed?
Yeah.
Well, all of the above. You know, there are certainly dietary things that can contribute to it, but alcohol is probably a biggie. If alcohol is a solvent and the fat that lines and insulates the axons that connect neuron to neuron is all out of fatty acids, cholesterols, and things, the alcohol is going to dissolve that. So you get a bunch of shorting out connections. So even though the neurons might be intact, the connections between them may not work because the alcohol slowly dissolves the connections. The nicotine causes vasoconstriction of these vessels, and so you can aggravate what's already constricted blood flow to the brain by a lot of smoking with nicotine. All the byproducts of smoke are also toxic to the neurons, so that'll aggravate it. Nicotine by itself, we use, or at least I'm using it to help counter the effects of dementia because it does stimulate new processing in the brain in short-term memory areas because it mimics acetylcholine, which is what all of the drugs they use right now are trying to address. They use things that stop the breakdown of acetylcholine in your brain. And neurologists, most people don't have any clue about this, but from a neuroscience standpoint, the acetylcholine in the brain coming from the forebrain, which is in the septum area, it stimulates or overrides GABA, which is inhibiting other parts of the brain. And if we can override that GABA suppression of our little stem cells that are desperately trying to regenerate and start making new connections and new memories, then suddenly these stem cells begin to flourish. So actually the effect of nicotinic acetylcholine to counter the inhibition that GABA has on these little nurseries of stem cells that are sitting down here in the base of the brain waiting to be told what to do. So now the GABA is off the table, and acetylcholine begins to stimulate these stem cells to become neurons and then to start making their little connections. So it's the nicotine you would think would contribute to vascular dementia, but in fact, it's having that acetylcholine effect to stop the GABA suppression of these neural stem cells to evolve into brain. So I think that's how it's working, and there's very little known studies, but I think that's how nicotine may be providing some benefit, some prophylaxis for dementia.
Nice. So I'm just going to repeat what you said, and you kind of button it up because you were talking about. So in the brain, we've got these nurseries of stem cells. So we've got these little areas with these baby cells that are they're just waiting to be told what to do, become a new neuron, become a myelin sheath around a dendrite or an axon. So once, and they're in these nurseries, and GABA is suppressing them from coming out and becoming what they're supposed to be.
Yeah.
But nicotine tells GABA or forces GABA to stop suppressing them. They then come out, and then all the other factors that are going inside of the brain then tell those baby cells what to do.
Right. That's exactly right. So think of GABA as kind of a babysitter that won't let the kids out of the room.
Okay.
And now you've told you fired the babysitter with the nicotine, acetylcholine, and now the stem cells, we're free now. We can become neurons.
Okay, I like that.
I would think that there's some early warning signs that that people could start to watch out for. Like, I mean, forgetfulness is an obvious one, mm-hmm. but what are some other dementia warning signs people can watch out for?
Well, it comes in several stages. First you begin to notice that you're forgetting a lot more, or it's better. I'll give you an example. I saw a patient today, and she's really worried about her husband. And here's how her husband presented, and it's just been in the past few weeks. Mm-hmm. She's noticed over the past 12 months that he's getting a little more forgetful, and she can overlook that. But she's noticed that there's things that he's not doing that he normally would do. He would throw a bill in the garbage that he knew he should have paid. But she can overlook that because everybody's maybe make that mistake because there's so much junk mail. But then she began to notice that he was having some weight loss. He was getting a little more moody and a little more argumentative about things. And I think in this case, and I'm complicating it a little bit because apparently he had a fall and hit his head on the concrete, and he had trouble finding his way home.
Oh, wow. So he obviously had a pretty solid head injury.
Yeah, he had a head injury on top of this slow cognitive decline that she was noticing. So when he got home, he had cut his hand to the bone, was bleeding. When he got home, he was wiping the pavement off his face.
Oh, my God.
And he's got blood all over. So he peers at the door, and, of course, she's freaking. She said, oh, my God. And she's asking, what happened to you? Did you fall? No, I didn't fall. So he didn't remember even falling. So this is a pretty good head injury. So since that happened about 4 weeks ago, now his dementia has really accelerated. Now he is really unable to function. So it's complicated by the fact that he had this concussion superimposed on an already progressive dementia. But she's thinking, oh my God, the dementia's gone nuts now, and he's really having this dramatic decline. When in fact, it's really accelerated by the brain injury. So initially, you have this mild stuff where you begin to forget things like going to the kitchen to get water, and and then you slowly progress. Let's take the brain injury out of the way. All it does is tell you, wow, we jumped several stages overnight. Now he's having trouble remembering how to put his pants on. He's forgetting how to do any of the light work around the house. So she's having to take over everything. So that's kind of how the progression goes. And if you combine that with the fact that he's losing, he was 186 pounds before, and now he's down to 130. So he has no appetite. She fixed him just some scrambled eggs, and he ate like a third of them and just wasn't hungry. So you begin to waste away. This brain wasting away has now caused this to waste away, as well as physiology to waste away.
That seems like a pretty rapid decline.
Yeah, but in this case, this is a neat example because this is what you may see over years with normal dementia. But boy, that brain injury threw him like 4 stages forward in his dementia.
Yeah.
So, what is the difference between Alzheimer's and dementia? You had first started talking about dementia being this umbrella and how Alzheimer's is maybe one of the items that contributes to this overall dementia. And you have a theory that Alzheimer's is an inflammatory autoimmune process. Can you unpack that a little bit?
Yeah, this is, everybody just lumps everything into Alzheimer's, but there is a specific diagnosis of Alzheimer's, and it's kind of a moot point because you kind of all end up in the same place. And like we were talking about with this patient of mine, her husband. But Alzheimer's is specifically a genetic thing. So it runs in families. We've isolated the gene, these APOE genes, and APOE4 is the one that seems to be responsible for the super rapid decline of dementia. So, just a quick falling off. And back in '84, I think, this guy discovered this stuff in the brain called beta amyloid. And he noticed that in the pathology in dead patients that had Alzheimer's or dementia, he found that they had this substance that was just everywhere. And it was just this beta amyloid, this goo that kind of clogs a lot of things up. And as research went on from '84 on, everybody was blaming everything. Okay, it's this amyloid that's causing the problem. And all research from like 2000 on was focused on trying to figure out how to stop this beta amyloid, thinking that was the thing that was poisoning the brain. And it was unique to this genetic group of people that would form this beta amyloid, because a lot of dementias don't have beta amyloid in them at all. Like the vascular dementia may not have it at all. So
That's interesting.
So it's unique to Alzheimer's, but you can see smatterings of this amyloid in other dementias also. But the whole point about Alzheimer's was now we have a genetic group of people that definitely have this beta amyloid, and so we're going to blame it on beta amyloid. So all the research then focused on, okay, what drug, because everybody's looking for that one drug that will fix it. Because that's how the pharmaceuticals make money, right?
Yeah, the strep throat idea of finding new drugs.
Yeah, everything has to be a single drug, otherwise nobody makes money.
Yeah, it's too hard.
Right. So all the research went into that, and what's crazy is that I think there was like 6 or 7 drug companies, Pfizer's and Lilly, and everybody was focused on this stuff, and from 2000 on. And they were all trying to find this antibody to or some cure for this beta amyloid, and nobody ever found it. I think Biogen sank $18 billion into looking for this drug on this one immunotherapy, Aduhelm, and they were sure that was going to do it. They submitted it to FDA twice, and they turned them down in 2019. And all of those of us who are really neuroscientists and not just clinicians, and because my background is neuroscience and neurochemistry, is that tells me if you have 5 drug companies that have been looking at it for 20 years for something that will stop beta amyloid, and nothing has ever worked, even though it may have stopped beta amyloid, it didn't stop the Alzheimer's. So that means, well, that must not be the cause. So it's kind of like going back to the infectious thing. So let's say you have a bladder infection, and I prescribe for you an antibiotic, and it doesn't get better. Well, then okay, well, the bacteria that's causing the bladder infection is obviously resistant to that drug, that antibiotic. Well, that's where our minds went back in the mid-2000s, early 2000s. We go, well, obviously anything that stops beta amyloid doesn't stop the dementia, so it must not be beta amyloid. I mean, you just have to get to that conclusion. So in my mind, I'm thinking, well, there's a lot of things that go on in the brain and in our bodies that are autoimmune. Our bodies have generated an inflammatory response because it stimulated our immune system to go on attack. And I think that that's kind of a theory, but I think that it bears out because in the brains of these Alzheimer's patients, you see a lot of inflammatory cytokines and things, and we know that beta amyloid in itself is inflammatory. So I think the drug companies were on the right track. If we stop the beta amyloid, maybe we can stop some of that neuroinflammation, but it didn't work. So obviously something else is going on, and the cause is unknown. And that's disconcerting because we focused on the wrong cause for so long, trying to get that one drug, and the brain does not work like that, that we've lost a whole lot of time. And I think we've wasted a lot of time instead of looking at it from a neuroscience standpoint and not a profit standpoint. How can I make the most money off this one drug that I can cure Alzheimer's, which is like 50 million people worldwide and 10 million more every year. So how can I, if I get the drug for that,
Yeah, you're set.
And the money.
I'm set forever.
Yeah, you and your progeny for the rest of the time on the planet is
Right.
good. Is there a test for dementia? Like, is there a blood test for dementia?
No.
Okay, so imaging, is that the only way to really test?
Well, go back to that because there are some genetic tests you can do, and I think there's a lot of labs, especially like Stanford, I think is working on some things like that. They're looking at the genetic. I think Hopkins is doing a lot of work on that. I think Hopkins and Stanford are the ones that are really looking at the genetic part. So yeah, you can do a genetic screen. Nobody really does that because you already know it's Alzheimer's.
Right, but there's not a blood marker that you're going to see in the general population that's like, oh, this guy has vascular dementia or he's going to get vascular dementia.
No. You kind of know it though, because you've got if a lot of his other blood vessels are clogged, then you kind of figure that okay, that's probably vascular dementia. But what I do is I look at all the inflammatory markers because assuming that it's inflammation, let's look at anything in the body that is a marker for inflammation. Well, what is a marker for inflammation? Well, we know high sensitivity C-reactive protein. If that level is high, everybody has used that measure to diagnose the propensity to develop heart disease. And that's good because it is pretty sensitive to what's going on inside the artery pipes. But it also is a little bit complicated by the fact that other inflammation sources will also raise that level of CRP. So if that level's high, homocysteine is another.
What really is homocysteine?
Homocysteine, and C-reactive protein also, by the way. These are both proteins that are made in the liver.
Okay.
And for some reason, the liver gets a signal that there's inflammation out there. So it begins to crank out these two proteins, homocysteine, C-reactive protein, lots of others, but those are the ones that are really easy and fairly inexpensive to measure. Mm-hmm. When those levels rise, you know you got to go looking for something.
Okay. And then it's like, something's up. Let's check the main organs, heart, brain.
Right.
And then, okay. Because I've seen homocysteine on tests. I've seen C-reactive protein on tests. And I've seen them in my blood work. And I'm like, I don't even know what that is. But I know that you want it to be a lower number.
You do want it lower. And that's a complicated one. But let's just take C-reactive protein for a minute. The way I look at these inflammatory markers, particularly C-reactive protein, to me, that's the liver preparing to repair something. Because what happens when the liver gets inflamed and this C-reactive protein is being produced? When you get an inflamed liver, the thing that is increased in your bloodstream is cholesterol. So the cholesterol is used to go out there and make new cells, make new cell membranes, because all cell membranes are made of cholesterol. Mm-hmm. So the body is actually cranking out cholesterol at a much more increased levels or much more increased rate because it's preparing to repair. So and so it's the inflammation of the liver, I think, that is your first signal that there's inflammation out there. Now, it's not just dementia inflammation. I think it's inflammation on anything. So when you see guys with elevated C-reactive protein, you've got to think, it maybe the pipes are getting clogged because there's inflammation on the inside of the pipes, and so the body's making more cholesterol to get to smooth out the rough areas in the pipes where the lining of the arteries are inflamed. So the body wants to smooth it out with this nice little layer of slick cholesterol plaster. Everybody's beginning to think, cardiologists excluded because they're really into the cholesterol theory of heart disease, but almost everybody that's thinking scientifically is thinking, the cholesterol elevation is a precursor for repair, because the artery needs to plaster out that rough area inside the pipe.
I kind of want to say what you just said, because this took me a second to understand as well whenever I first started working here, was cholesterol is there to repair. Cholesterol, if your arteries are inflamed, or if they are the edges are not smooth to where the blood cells can easily pass through, cholesterol will go in and repair those, make them smooth. If your cells are damaged, then the cholesterol will go in and actually repair that. So a lot of people don't know what cholesterol is for. Mm-hmm. So it's there in your body to repair things that have broken down. So it's like duct tape. Right. Like you basically just use that. Right. So you use duct tape to go and fix everything. Then if you got too much duct tape, that's not a good thing. No. But if you use it specifically for the things that you need it for, then it can be used in a manner that's beneficial to the entirety. So I think that when people say, well, I just need to get my cholesterol lower, it's without understanding why you have cholesterol in the first place, why your body needs to be using it in a repair process. Right. So,
fun fact about duct tape is that out of the hundreds of uses for duct tape, duct repair is actually not one of them.
I think that's true.
Yeah, you're not supposed to use duct tape for ducts.
You're supposed to use aluminum.
Yeah, the
tape.
Aluminum flashing tape.
Right. And I wish we could use that inside a pipe of an artery, but we can't do that.
Sure would be nice. You just kind of pull the backer off and stick it on. Right. But like iron it out a little bit.
To follow up on your thought, and it's exactly right. Let's extend that on. So let's say on the inside of your pipe, something has caused an irritation in the wall of that pipe, in the artery wall. And now this blood that's cranking through there at like 120 millimeters of mercury, which is a pretty high pressure. Now it's got this eddy in the flow, so it's going to go instead of in a slick, smooth down the pipe. So the body knows that's not a good thing. So some message goes to the liver, and the cholesterol begins to want to plaster that smooth, so it's a slick surface. And it could be anything. It could be too much high blood pressure, so the artery's going like this with every beat of the heart. Or it could be an allergy to foods. You could be allergic to God knows what that you're eating. And again, that kind of brings in the diet, which I don't want to go into.
Think about allergy to foods. That's crazy.
Yeah, that is. So let's say you cause inflammation inside the pipes. Now you've developed these bumps along the walls of the arteries, particularly at corners where, like in the coronaries, the blood's cranking around a hard turn, and it's like a car. It's just going really fast. So there's the potential for a wreck or a lot of more damage to the wall.
A lot of momentum going in one way.
Right.
Yeah. Wow.
And cholesterol. Sorry, are you heading down a path? Sorry, I didn't mean to.
Well, yeah. That's all the cholesterol is trying to slick it up, and so everything slides through smooth. But if you don't stop the inflammation, it's going to keep trying to plaster out a smooth surface in there. So eventually, the cholesterol keeps building up, and the wall of the artery keeps encroaching on the lumen of the artery. And pretty soon, you got a clogged pipe. And everybody says, "Oh God, it's cholesterol." No, it's not like that. You have not stopped the inflammation that caused the problem to begin with, because we focused on cholesterol. You haven't done anything about the inflammation.
Right. Yeah. I'm sorry. My cardiologist talks a lot about getting your inflammation levels down, especially with how you eat and all that. But he doesn't really subscribe to the whole statin cholesterol drug thing.
You have a smart one.
He's pretty good. I like him.
Here's the thing about that, because the diet does play a role here. there's things that we doctors don't really understand very well either, unfortunately. But we have inflammatory cascades in our body. So there's this cascade called prostaglandins. The body makes prostaglandins in response to inflammation. And what you want to do is block that prostaglandin cascade so you can suppress the inflammation. Well, guess what does that? Omega-3s. Omega-3s, so fish oils, they stop the body from this eicosanoid prostaglandin pathway that brings about the inflammation molecules, and so the eicosanoids are suppressed by omega-3s. That's why a diet is so cool. That's why omega-3s have so much potential to stop the inflammatory response. So instead of worried about how much cholesterol you got, you should be thinking, okay, what's my high sensitivity C-reactive protein? What's my homocysteine level?
Yeah. And obviously those you can see on blood tests.
Right. That's great information. And how often should you be tested for those? Is it just when you're feeling or you're needing to go into the doctor and say, oh, something's off? Or should that be kind of a regular thing to have your inflammation measured?
Yeah, like a once a year checkup.
Right.
Like
Yes.
Let's look under the hood, check the oil.
Yeah.
Yes, it should be part of every lab visit. And what you'll see when you go into the doctor, cardiologists are getting pretty savvy now. They're starting to look at inflammatory markers. But what you'll normally get at your routine PCP is you'll get a CBC, which is what your red blood cell count is and all of that. And they'll do a chemistry, which will show you what your electrolytes are and what the kidney function's doing. But they don't look at the stuff that has potential for long-term destruction of your body, like inflammatory markers.
So you need to request those specifically. So as your own health advocate, so we should have a list of things that we should be bringing to our PCP and saying, I need these added to the blood test that you want to give me.
That's right. The unfortunate thing is I had a woman that goes to her gynecologist, and the gynecologist, you don't need to be on all those vitamins that Dr. Clark put you on. That's just wasting money, and it's also making expensive urine, and which is just an indictment right there. She needs to find another doctor right off the bat.
Yeah, it's extraordinarily short-sighted.
But, yeah. So omega-3s, that should be high on the list of anybody that has a family history of heart disease and clogged vessels in their dad or their brother or sister. And so instead of accusing the patient of taking wasted vitamins, they should go home and read about them.
Educate yourself.
Right.
Yeah.
The doctor should go home and read about
That's
them.
the problem. Yeah. That's a big, bad problem.
Is that they think that they're done learning after
Yeah,
they're done
med
with
school.
med school.
Finished.
Yeah.
So you brought up homocysteine.
Mm-hmm.
Homocysteine is that other inflammatory, easy and cheap to get on a blood test. So homocysteine is, again, one of those proteins that gets fabricated by the liver in response to inflammation. Homocysteine, you can control that. We talked about controlling C-reactive protein with omega-3s, fish oils, but we can also control homocysteine levels by methylating them. So a methyl group is a carbon with 3 hydrogens on it, and it rides on something else. It rides on a molecule. And the easiest thing for it to ride on is folic acid. So you see in your B vitamin bottle, you see B12, B6, B4, B2. So you've got all these B vitamins, but one of them is folate, which is B9. If you look for a B vitamin, look for one with methylfolate. So this methyl group of 1 carbon and 3 hydrogens is attached to that that folate, and it rides in. So what the body then does, this is really cool, the body takes the methyl group off of that folic acid, and it sticks it on homocysteine, which converts homocysteine from an inflammatory molecule to a building block protein, a methionine. So methionine is the substrate, it's the building block protein, which generates all the other proteins in your body. So now with just methylfolate, instead of just folic acid, you have methylfolic acid. Now the methyl group can contribute to rebuilding the body, repairing cells, and dropping the inflammatory markers.
That's wild.
Simple, and it's just straight biochemistry.
So when you go and you buy your supplements, read on the back, look at
for
the supplement
methyls.
label, and make sure it says methyl
Folate.
folate.
Correct.
Yeah, methyl B12.
That's methylcobalamin.
Yes.
Right. So
Correct.
just look for the methyl groups because the body responds better. So just kind of an add-on question. What would be your list of inflammatory markers that you need to look for in your blood work?
Those two.
Those
sure.
two. Homocysteine, C-reactive proteins.
Okay. I have a quick question. I know I've got it listed as you on here, but I want to kind of move into the this mitochondrial gatekeeper.
Yeah.
So there's something that was really kind of neat called this new mitochondrial gatekeeper, this VDAC1 out of Israel. What is this, and how does it work? I'm going to assume that it has something to do with this destructive cascade, the destructive sequence. So can dementia be reversed? And what is this VDAC1 out of Israel?
I think that's probably one of the key studies that have been done in the past, really the past 12 months. We've known about this protein called VDAC1. So this VDAC1 appears to have a normally fairly low level because you don't normally need it. But in areas where, and the most of the work that's been done has been done looking at the beta amyloid, this thing we're talking about with Alzheimer's. When the beta amyloid gets in the cell, it really does crank up inflammation. And the VDAC1, when it increases, it stops the mitochondria, which is making the energy in the cell, from working. So if the mitochondria is not making energy in the cell begins to gasp and wheeze because it's like it's in its 24th mile of a marathon, and it's going, wait a minute, I can't go any further, and it quits. And then you get some Gatorade and go home. But the mitochondria doesn't have that option; it just gives up, it ghosts and dies. So when that dies, then you lose the cell, and then that begins that destructive sequence in the cell, because once the cell dies, then it ruptures, all its insides go out, and it damages the cell next to it, because all these free radicals, they go out and they attack the membrane of the cell next to it. That cell dies. Now you've got this cascade of cell to cell. You have just this ever enlarging hole in the brain, and in any cell, all these cells work the same. So the VDAC1 seems to if you suppress it, it keeps the mitochondria alive. So let's say that we have this inflammatory response that normally the VDAC1 begins to rise, the levels, and the mitochondria are dying. So if you block that and you suppress the VDAC1 molecule, then the cell survives. So there's a neat thing about that. So the mitochondria lives, it keeps going, and the cell lives. So what these guys did is they tested it on this genetic group of mice who were bred that were models for Alzheimer's. So we knew that they were going to get Alzheimer's. So they started giving them this compound, this kind of an experimental compound, and it suppresses the VDAC1 protein. So it turns out when they chopped up the brain and looked at it, that the cell was survived and the mitochondria was functional. So that right there is going, wow, that's interesting, because this is a mouse that would normally get Alzheimer's and these cells would explode.
Yeah, you had already started seeing all of the beta amyloid already in there, and
right.
you would have seen.
Yeah, under the microscope, you would have seen.
Yeah, and the big holes in the brain matter.
Exactly.
Well, that's wild.
So they didn't see it. So then they took these mice, and they had these tests, these behavioral tests. So they'd stick them in a water maze, and the idea is they swim around until they find this little platform, and they get up on it, and they survive. Normally,
Do
so
they
it's a
die?
learning.
Do they die if they don't find it?
Yeah, well,
Stakes are high.
No kidding.
Got to figure
Yeah,
that puzzle
it's like-
out quick.
so normally these mice, as they progress in their dementia, they can't find the thing, and of course, either they have to rescue them or they just drown. So we want to assume that they rescued them
Yes.
for future. Yeah.
Yes.
And but I don't know how that works. But anyway, so what they found was if the mice did not get the VDAC1 suppressor, they would drown or be rescued, have to be rescued. But the mice that got the VDAC1 suppressor protein, they found the little platform just like a normal mouse that was not bred for Alzheimer's. So they overrode this genetic predisposition
Wow.
for Alzheimer's. I thought, oh my gosh,
Man,
that's
the Israelis. The
that
Israelis,
is
man.
amazing.
That is impressive.
Those guys.
So it's kind of a preliminary set of research. So they didn't not only look at the brain to see that the brain was preserved by this thing that stopped that particular protein, but they also did the behavioral test that said not only were they able to preserve their brains, but they were able to learn and remember to get to that platform. So it's like reversing Alzheimer's.
That's wild.
So, oh my, when I read that study, I thought this has got to be like a landmark study. So what then blocks VDAC1? So now I'm thinking, okay, what does block VDAC1?
Yeah.
I mean, it doesn't have to be that one protein that the Israelis came up with. Is it in a food? Is it curcumin? Is it
Yeah. Yeah. What naturally occurring
question.
exactly?
substance
So
can...
I'm not at that point yet. So
That's-
eventually, hopefully,
jeez.
I'll dig into that.
Yeah.
Let us know what you find out, because
We'll be very curious about that.
Right.
I guess I'll ask a personal question, and this probably relates to other individuals who are younger. For young people who might be worried about having dementia themselves, that have family members that have shown dementia or Alzheimer's type symptoms, what would you suggest that they do to try and stave off what might be genetically predisposed to them, but what could they be doing to just try and get ahead of it?
Well, that's a really good question, because what you're asking, is there any prophylaxis that I can take to prevent my brain from following that same inflammatory sequence of events where the cell membrane explodes and you start cascading and start losing more brain? And we know that's what happens because we do MRIs of these Alzheimer's brains, and there's a lot of brain shrinkage, which means you've lost a whole lot of mass, and that mass are cells and synapses and pathways and fiber tracts. And that's a great question. And it goes back to that destructive sequence that I've referred to before. Membrane ruptures, kills off the cell, it leaks. You got to scavenge those free radicals, otherwise you kill off the next cell next to it. If it leaks out its neurotransmitters, you got to scavenge that or block that neurotransmitter so it doesn't kill off the adjacent cell. You got to stop the cytokines, the inflammatory cytokines. We learned all about that in the pandemic cytokine storm and stuff. So how do you stop that process? And in you're lucky because you don't have the genetic predisposition for that. You don't have the APOE4, so you're lucky there. So let's say this might be controlled by diet. And here's kind of an interesting story, and I hope he doesn't mind me saying this, but a good friend, Tony Mizzatano, his good friend was Franco Harris, who was like
A football
Yeah,
player.
famous catch.
Yeah.
big
The
deal.
Steelers.
Yeah.
Big deal, and a heck of a nice guy. And he told Tony one time, Tony asked him, well, how'd you not get CT? Because this cumulative traumatic brain injury, which is like Alzheimer's, but from repeated hits to the head. Mm-hmm. And he said, Tony, I just ate blueberries all the time.
No kidding.
And I thought, that is genius.
Wow.
So the antioxidant effect of blueberries was playing a role in scavenging all these free radicals that are released by the brain damage that he got every time he got hit.
Wow, that's
And
crazy.
I thought, that's brilliant. So, so your question is good because I think you can prophylax with diet. I think antioxidants in your diet You got vitamin C, you got vitamin E. Your body makes something called alpha lipoic acid, which is your own antioxidant that the body creates. It scavenges those free radicals. And in fact, it actually renews the antioxidant abilities of vitamin A, vitamin C, vitamin E. So it kind of keeps doing double duty. It scavenges free radicals, and then it helps the vitamin C come back as an antioxidant as well.
Oh, that's cool. So it can juice them back up and make them antioxidants again, even after they've kind of puttered out.
Yeah,
that's
exactly.
cool.
It's incredible.
So you've got all that. So you can take those. You can take C. You can take E. You can take all that. And you can take alpha lipoic acid, easily available. It's cheap. But you can also, and CoQ10 itself is an antioxidant, omega-3s. But you also have curcumin, which is turmeric. It's a great anti-inflammatory. So you can take that. So you have a diet that's like a Mediterranean diet. My French parents, they lived until their mid-90s. They did fine. They ate the Mediterranean diet.
Sure.
Something to be said for that.
Lucid to the beginning, to the end.
I think we should just move to the Med.
I think we should move to the Alps.
Seems
or
to be the
to
obvious
Corsica.
next step.
Corsica.
Ooh,
We need to go to Corsica or Sicily and just live on that diet.
And eat bouillabaisse every day.
Yes. I think we should travel around and make sure we know exactly where we want to stay first.
We probably should take
Correct.
a boat.
Well, you want a variety of diet. You don't
Right.
want to just lock into bouillabaisse.
Absolutely.
That's the whole point of a lot of the things we do in our supplementation is we're trying to supplement with super antioxidants and support that mitochondria so we keep it alive. Kind of like the Israelis. How do you keep the mitochondria? If you can keep the mitochondria alive, you can keep the cell alive. So that's part of our supplement program. And then you try to suppress inflammation. So we put things in there that will stop inflammation. All right, so let's talk about one more thing. Not one more thing, but at least I want to touch on this because this is every bit as important. We talked about nicotine and acetylcholine and how the acetylcholine seems to fire the babysitter of GABA so that the stem cells can now morph into neurons and start making their little connections. And I think that's really cool that it does that. People with Parkinson's, they get dementia. And they also get to the point where our drugs, which is L-Dopa, which is replacing the dopamine that is no longer being produced in the brain, which is why they tremor and why they get all stiff. Those neurons finally give up the ghost. I don't care how much dopamine you give them. Eventually, they can't. They get resistant to it, so they get stiff, and the Parkinson's takes them out, and they also become demented. And what's really neat, and I think it adds more power to my thoughts about how nicotine works as far as getting the stem cells to morph into neurons. Not only does nicotine also increase the dopamine output of the cells that are making the dopamine, so it's actually stimulating your own brain to make more dopamine out of the cells that make dopamine.
Positive.
Yes, so it's goosing them.
Yep.
But it also seems to prevent the dementia that comes from long-term Parkinson's. And it also prevents you from being resistant to the L-Dopa medicine that we're giving them.
This is the nicotine.
Yes. So acetylcholine, nicotinic acetylcholine will stop you from getting resistant to L-Dopa.
Wow, that's big.
And it will stop the dementia that, assuming that
That's coming down the road.
down the road.
That's pretty crazy.
So you see Parkinson's patients, and this is something that you recommend, something that you've seen as being positive on your patients.
Yes.
Is that?
But I can't take their brain out and look at it.
Right.
No,
and
they're
know
pretty resistant
exactly.
to doing that. Yeah, so I would be too. Is this similar to this GABA?
Some people wouldn't notice
No.
if you were to take their brain out and look at it. Politicians, lawyers.
Yeah. Was that similar to the GABA A, GABA B thing that we were talking about before?
Oh, yeah, that's a whole different subject, but there's a neat one.
I wanted to ask you a question about GABA A and GABA B, and what are the differences between the two, and what do you use them for?
Yeah, GABA comes in the little receptors on these neurons come in different forms, the GABA A and GABA B, easiest to understand. So it's a different type of receptor, but it's still GABA sensitive. So GABA A seems to stimulate the morphing of these neural stem cells, which we all have. I don't care if you're 90 years old, you still have these neural stem cells in your brain. GABA A seems to be the one that stimulates these neural stem cells to morph into brain cells and start making the network happen. And so GABA B is great because it has a lot of different functions, but here's what we see in rehab medicine, and it's unfortunate because everybody is so anti-Valium in the world because it's an addictive drug. I'm scared of that drug, and the state doesn't want you to prescribe Valium. And yet, so everybody prescribes this drug, baclofen. Baclofen stimulates the GABA B receptor, and it does decrease the spasticity that you get, the tone. After a stroke, you get this.
Yeah, they look like they're kind of tightened up.
Yeah.
Like a knot.
Yeah, and you try to get it out, and it comes right back. So that's called hypertonicity. If you give something that will stop that tone, suddenly there's some voluntary movement hiding in there. You don't know it until you get rid of the tone.
It's been masked by being completely stiff and locked up.
Very well said. That's exactly what happens. So the goal in these rehab patients, and doctors don't do this much, unfortunately, but if you know the neuroscience behind it, you go, oh man, that would be good to try. So you drop the spasticity and the tone in that arm, and suddenly you begin to see this arm begin to move. And it's not really great. It's not functional yet, but then you start working with the therapist and you start getting some movement back.
Which is way more than what you had to begin with. I mean, you didn't even know that there was possibility of movement there to begin with, but now you're actually getting some gain of function back.
Exactly. And otherwise, they go to a nursing home and they die. They get infected and they die. Or you can know the neuroscience and you can fix them, and they can go home with their families, and they might even actually be able to feed themselves. So here's the thing about baclofen and Valium. The generic is diazepam. Diazepam and baclofen work on two different GABA receptors. Baclofen on GABA B, Valium diazepam on GABA A. GABA A has the same benefit. Actually, it works better on tone, but it also has this benefit of stimulating stem cells to morph into neurons. GABA B does not. So if you use baclofen, you're going to get some tone release, but you don't get anything else.
You don't get any of that great ancillary other benefits.
You don't get repair.
Right.
And that's what diazepam will do. It will help the brain repair.
And people are just worried that they're going to get them addicted to Valium.
Right. They're so scared of Valium. Oh, I don't want my mom to have Valium.
Y'all need to change that.
State regulatories will go, oh, you're writing too many prescriptions for Valium. Well, I got strokes and spinal cord injuries. I mean, these people are so toned. I mean, they're pretzels. I can fix that. And not only can I fix that, but with therapies, I might actually be able to get voluntary movement out of that arm.
So what are GABA A and GABA B receptors? Like, what can you explain where those exist and how Valium and baclofen actually make their way to those receptors?
Yeah, it's kind of complicated, but let's use the old-fashioned telephone system. So you have a wire that connects your phone to your neighbor's phone. And back when we had party lines, you could find out what Ms. Bourdelawn was doing, Friday night. So you have this wire that's a direct line to Mrs. Bourdelawn's phone. But let's say you want to stop that signal from getting there. So in the brain, you have something called an interneuron or a presynapse. So some other wire comes in and it connects to that wire, and it stops the transmission down the wire, so it shuts it off, so you can't hear Mrs. Bourdelawn, so you don't know what she did Friday. So that GABA receptor there is inhibitory on the the main motor neuron that's going to the muscle. It stops the muscle so it's an inhibitory synapse. So what you want is something to stimulate that GABA receptor so that it will stop that tone that's making that.
Gotcha.
That's a pretty good explanation.
Yeah.
Ms. Bourdon, oof,
Yeah.
she had some gossip, man.
Well, I bet. But the party line.
Here's another question. You talked about how GABA.
I don't know Miss Bourdon at all. I have no idea who Miss Bourdon is, but that's just a name I'm
She's
using.
probably dead now.
Well, even if she
didn't
but
exist. That was the name that
I don't know that even if it were a person, I don't know if she's doing anything bad on Friday.
This is a
completely
made-up-
fictitious person.
Purely-
Dang it, man. I was
Purely
all-
for purposes of
Man, I got to tell you, I had this whole like image of her in my head. Mm-hmm. Yeah, she's probably like the buxom one in the neighborhood.
Yes, good looking.
Probably divorcee. Mm-hmm. Yeah.
Mm-hmm. Kids left the nest, maybe.
Yeah, drank a lot of wine.
No, she didn't even exist. I'm just using that name because all of those Cajuns. you
Bourdon
never
was a
know what they
fox. Foxy Bourdon.
The whole point of that conversation is that, and I'll go a little deeper into it. You have voluntary tone, which the cortex says, I want to move my arm. So it sends a signal from the thinking cortex down into that muscle, and it makes it work. But then you have this involuntary tone that we don't have to even think about. Why are you sitting up straight?
Or breathing.
Or breathing,
Yeah.
right? So that's this involuntary whole different system of motor activity that just maintains your posture without you thinking about it. While you're standing in the grocery line, you're waiting on that stupid woman with all the coupons.
Or the coin purse.
Digging into her coin purse. And you're
Stop
going,
digging
"Christ,
your
it's ever
coin
gonna
purse, lady.
So you're tired, you want to go home. But
You're writing a check?
It's a Hallmark card. God.
write a check for Hallmark.
They have gone up. They're like $7 or $8.
Oh, they are.
I
Unbelievable.
mean, you
And
could write
nobody
it
ever
there.
reads the dang things. I don't get it.
Luckily, my 8-year-old does.
Oh, she reads them.
Yeah, she'll read them.
Okay, I'll still send her cards.
Yeah.
Yeah.
So the point is that you have this involuntary postural motor system that is constantly active, maintaining your upright position at the grocery line, waiting for your time at the cash register, and you don't even have to think about it. But if the involuntary system is overactive, because this system is stroked out because of your stroke that you had on this side. So this whole arm doesn't work and it's all tightened up. The reason it's tightened up is because the involuntary system has no control. It is completely submissive to the voluntary, but the voluntary is not working. So now you've got the involuntary control taking dominance. So you've got to stop that involuntary motor function. So that's what Valium and diazepam, baclofen, whatever you want to use, stops that involuntary system from going down there and making the muscles contract constantly. So now there may be a few cells up here that are left over that might actually be able to voluntarily control that arm. So now you've shut down this system so that this system can break through and do some voluntary motor. And that's what Valium does so nicely.
Wow.
And we're making new connections and new neurons.
Right, and building a new brain.
Correct.
That's wild.
That's exciting.
Well, it seems like that's an obvious thing to use. I wish the regulators would get out of it.
Nobody needs to take charge of this except the doctors.
Right.
A high school grad bureaucrat has no business
No.
being involved in anything we're doing.
Yeah. Well, I think that pretty much wraps this up, man. I really appreciate you coming by again and just giving the drop in the knowledge bomb.
We sort of went far afield from dementia.
We did. But that's kind of what these things are about.
Yeah, I think it opens up the discussion to talk about neuroscience that nobody ever thinks about.
Well, thanks, Doc.
Okay,
All right, everybody.
enjoyed it.
We had fun.
Thanks.
That's a wrap.